Consider a relay system that has 4 components. It's basically 2 in parallel and 2 in series. Okay, so it's going to look something like one of the paths is parallel. The other one has 2 components in series. So we'll call this 1, 2, 3, 4. And let's say that the probability that each component works is 0.9.
Okay.
And they work independently. Okay, find the probability that the system works.
So if either 3 or 4 fail, then it doesn't work. But if 1 or 2 fail, one or the other, it does work.
What are you calling A and B?
Oh, sorry, 1, 2. Already those are all resistors, right? That's just like, I'm just gonna call them all R's and
Sure, if that makes you happy.
yeah, just see.
Good. So your concept is there. We just have to translate that into statistics. So you actually said it correctly as well. You said that 3 and 4 need to work. 1 or 2 need to work, or both. And that's the best way to look at it. So because, well, let's look at this path first. Let's look at the bottom path. So if I'm going down this path, what's that color? I'm going down this path. If 4 works and 3 doesn't work, it's not going to happen. If 3 works and 4 doesn't work, it's not going to happen. They both have to work to get across, right? So probability, if you want to call them resistors, that's fine. 3 and 4 has to occur simultaneously. Correct?
Okay.
So that would be, they're independent of each other. So that would be what?
So since you have to multiply it.
Good.
So point
times. Okay. So there's the bottom path. We'll call it bottom. Now for the top half, what we do, especially the top part, is a little different. The top part is going to be 1 or 2 or both, which means that they have an intersection, right? It's going to affect our formula a little different. So instead of doing the multiplication, how do we do probability for events that are intersecting? So we can either have this path, the bottom path, or both paths would result in the circuit working. So because there is an intersection, our probability for R1 and R2 is going to change a little bit because of that intersection. We're going to use this formula. They're not mutually exclusive. It's not one or the other. There is an intersection. You understand what I mean by that?
You said they are. Wait, can you repeat that?
They are not mutually exclusive. What does it mean to be mutually exclusive?
Either one or the other.
Okay. So 3 and 4 are they? 1 and 2 are they mutually exclusive? No, you told me at the very beginning it could be one or the other, or what?
Or both.
Okay. So because we have both like that, we have to use this formula. Now, because of this equal sign, this is interchangeable. So we can either have the intersection here, or we can flip around and have the union here, which is what we're actually looking for, and the intersection there. Just solving the equation. Add that over there, subtract it over here.
Okay.
Are you with me?
Yeah.
Okay. So now if we want R1 or R2, we just plug into that, and we. Okay. So are we done? Okay. That's if they both had to work simultaneously, right? But what we're saying is that our final answer should be that the probability of the top or the bottom.
Oh, yeah.
Not and.
I see. Yeah, yeah. So it would be probability of the top plus probability of the bottom minus probability of the top and bottom. Okay. So I'm gonna write this down.
Wait, something fishy. Hold on. Oh, no, that's right. I was about to use the wrong formula. So because their top and bottom can work simultaneously, they're not mutually exclusive. We have to use this formula again here. So it should be probability of top plus probability of bottom minus the double counted intersection. So that would be top is 0.99 plus bottom, which is 0.81, minus intersection. How do we do the intersection?
Multiply them, so 0.99 times 0.81, which is 0.8019.
This one's 0.80?
Yeah.
19? Okay, so then when you do all that together, what do you get?
After all that, you get 0.9981.
Okay, so the system's going to work most of the time, it looks like. Got it?
Got it. Okay, so I just